This is a presentation of the paper Random Order Vertex Arrival Contention Resolution Schemes for Matching with Applications. This is joint work with Fu Hu, Zhihao, Jingzhao, and Qianfan. We first introduced the query commit setting for maximum weight bipartite matching. Such matching problem was first considered in query commit model by Chen et al. In this setting, there's a bipartite graph. For each edge E in that graph, there's a tuple WE and PE. WE is the weight of that edge, and PE is the probability that edge exists. In the beginning, you only know WE and PE. You don't know about the realization of that edge E. Namely, you don't know whether this edge E actually exists or not. Then you may pick an arbitrary order and query those edges. It's called query commit setting because if you query an edge and that edge exists, you must take that edge. For example, here we can first query the edge between vertex 1 and vertex 5, which has weight 10. And that edge exists. Then we must take it in our matching and we get utility 10. After we take the edge with weight 10, we cannot take the edge with weight 7 between vertex 2 and vertex 5 because they share the same endpoint, namely the vertex 5. Then we may query the edge between vertex 3 and vertex 6, which has weight 8. And that edge does not exist. Then we query the edge between vertex 4 and vertex 7 and get utility 6. Finally, we query the only edge left in this graph, and which exists. So we get a total utility of 20. In query commit setting, we are comparing the performance of our algorithm, namely the expected utility of our algorithm, to the expectation of the offline optimal, which is the expectation of the maximum weight matching in that realization. There's a closely related setting called the price of information setting, which was introduced by Singler. In such setting, for each edge E, there's a distribution dE and a cost of information pi e. Namely, you have to first pay the cost pi e before you query the edge and get its edge weight. But now, when you query an edge, you don't have to commit to it. You may query a few edges and pick the maximum matching among those queried edges. For example, here, we first query the edge between vertex 1 and vertex 4, whose edge weight is uniformly distributed between 0 and 8. And then, to query it, we must first pay a cost of 2. After the query, we know the realization of the edge weight is 5.5. Then we query those two edges adjacent to vertex 5 and pay the cost of 3 and 1 respectively. And we get their realization. And after these queries, we decide not to query the only edge left. So our utility is the weight of the maximum matching among the queried edges minus the total cost we have paid for the information. For both query commit model and price of information model, Gomez, Kell, and Svensson proved that for bipartite graph, there's a 1 minus 1 over E approximation algorithm for maximum weight matching. In this paper, we extend their result to general graphs and prove there's a 8 over 15 approximate algorithm for both models. Our results relies on extending random contention resolution schemes to vertex arrival, which we will introduce later. Contention resolution schemes solve the following problem. Given a set of n elements, where each element I is active independently with probability xi, and we have the guarantee that the expected number of active elements is less or equal to 1. Then, for a contention resolution scheme, one is required to select at most one element that is active. A contention resolution scheme is said to be alpha selectable if any element I is selected with probability at least alpha, conditioning on that I is active. For contention resolution schemes, these elements arrives in offline, and one can see their realization and make the decision. For random contention resolution schemes, these elements arrive online in uniformly random order. Upon the arrival of an element, one must decide irrevocably whether to accept that element. The main idea in GKS is as follows. In both query commit and price of information model, they write down an LP relaxation of the offline optimal and then solve the LP. Then they prove the optimal solution of this LP has some good property, which we'll introduce later, so that the profit secretary can be used to run such LP. So based on the profit secretary problem in bipartite graph, we can design online algorithms for both settings, which have the same approximation ratio as profit secretary problem, which is 1 minus 1 over E. Generally speaking, this is a reduction from these two problems to the profit secretary problem. However, we don't have a good profit secretary algorithm in general graphs, so these results cannot be directly applied to general graphs. We first observed that using similar ideas, we can also obtain a reduction from query commits and price of information model to random order contention resolution schemes. In bipartite graphs, the same result as GKS follows from 1 minus 1 over E selectability of RCRS. In our paper, we proved that there exists a 8 over 15 RCRS for general graphs, which we call random order vertex arrival contention resolution schemes. So based on this, we can get a 8 over 15 approximate algorithm in both query commit and price of information problem. Now let us briefly review the techniques in GKS and try to generalize them to general graphs. Here we present them for query commit setting. The price of information setting is more or less similar. The first step is to consider an LP relaxation of the offline optimal. That is the expectation of the maximum weight bipartite matching. Here, XE is the probability that edge E is in the maximum matching. So our objective here is the summation of XE times WE, which is the expected weight of that maximum matching. For each blue vertex V on the left-hand side, let F be the subset of edges adjacent to it, like this. Then FF is the probability such that at least one edge in F exists. For example, in this specific instance here, f of f is 1 minus the probability that all three edges do not exist. Since these three edges cannot be selected at the same time, the summation of their XE equals the probability that any of them belongs to the maximum matching, which should be smaller than that of f of f. This observation gives us the first constraint on the right-hand side. Furthermore, for the green vertices on the right, in any cases, at most one edge adjacent to it belongs to the maximum weight matching. This gives the second constraint. Therefore, we can see the optimal of this LP upper bounds the expectation of offline optimal. Let the optimal solution of this LP be X star, and suppose delta V is the edges adjacent to V. Then there's a distribution dV over the permutations of delta V, such that if we draw a permutation sigma from it, then each edge E is the first edge that exists in sigma with probability exactly X star E. This lemma follows from the submodularity of F. So let us first assume that this lemma is correct. Then, for each blue vertex, we can sample a permutation sigma from dV, and then query the edges adjacent to it in the order of sigma, and activate the first EI that exists. So by the lemma before, each EI is activated with probability exactly the same as the optimal LP solution. So for example, we first query the edge between 1 and 6, and it exists, so it is activated. We do this for each blue vertices. Each of them activates one edge. However, some green vertices may have more than one active adjacent edge now. So therefore, it has to pick one among them. Now, this is exactly the problem that contention resolution schemes solve. We randomize the order of blue vertices and model this as a random contention resolution scheme. Specifically, each green vertex here is an instance of random contention resolution scheme. That there are some edges adjacent to this green vertex, and each edge is activated with probability exactly XE, and the green vertex has to pick one of the active edges. This is a problem that RCRS solves. The validity of this RCRS instance follows from the fact that for each green vertex, the probability of adjacent edges being active sum up to at most 1. And the 1-1/E approximation ratio follows directly from the selectability of RCRS. Note here, the green vertex selects one of the active edges adjacent to it. At first sight, this may seem a little bit inconsistent to the query commit setting, because you have to commit to the edge that you query. However, this problem can be solved by some tricks, and these two can be made consistent. Now we try to extend these ideas to general graphs and motivate our definition of vertex arrival. The first step is to write down the LP relaxation. Here, let delta V be the set of edges adjacent to V, similar to that of bipartite graph. For each vertex V and subset F, summation of xe for all E in F should be bounded by f of F. And therefore, we can write down the following LP, which upper bounds the offline optimal. The second step is try to generalize our random contention resolution scheme. Since this is no longer a bipartite graph, now we, instead of randomize only the arrived order of the blue vertices, now we'll randomize the arrived order of all the vertices. And then let delta prime V be the edges from V to those vertices that arrives earlier than V. Similar as the bipartite case, for all vertex V, there is always such a distribution dV, where when vertex V arrives, we sample sigma from dV for all V and activates the first edge in sigma that exists. For example, here the edge between 2 and 3 is activated when 3 arrives. Then upon the arrival of each vertex, it may activate at most one edge to the vertices before it. For the edges to the vertices before it, each vertex V here acts as if it is a blue vertex in the bipartite graph. And for those edges to the vertices behind it, the vertex V acts as if it is a green vertex in the bipartite graph. However, here for these two kinds of edges, each vertex can in total take at most one active edge adjacent to it. This motivates our definition of vertex arrival random order contention resolution schemes. Formally, in this setting, there is a graph G such that each edge is activated with probability xe. We require the summation of all adjacent xe to be smaller than 1 for each vertex. The vertices arrive uniformly in random order. When a vertex arrives, all edges between it to vertices that arrives before its arrival, these edges arrives in a batch. Among each such batch, at most one edge is active. Therefore, the edges in the same batch are not independent. For example here, first vertex 3 arrives, and then 2 arrives. Then the edge between 2 and 3 does not exist, so it is not activated. Then vertex 1 arrives. It has 2 edges, to 3 and 2 respectively. These edges arrive in the same batch, and here only the edge to 3 is active. Finally, vertex 4 arrives. In this batch, the edge between 2 and 4 is active. Like in each batch, only one edge is active, and these edges, whether they are active or not, are sampled correlatedly. The performance guarantee we wish is still C-selectable, namely each edge is selected with probability C conditioning on it is active. We have shown that maximum weight matching in query commit model can be reduced to such vertex arrival random contention resolution scheme. Then we present our algorithm for solving this vertex arrival random order contention resolution scheme. It mainly contains 3 steps. First, adding dummy vertices to make the graph one regular. Second, do some pruning to shrink the probability of some edge. And third, run the greedy algorithm. We now explain each of them in detail. First, we transfer the graph into one regular graph. We do so by introducing dummy vertices and edges. Then, to avoid a single edge occupies too much probability that hurts the selectability of other edges, we prune the graph by shrinking the active probability of each edge. Namely, when edge E is active, we ignore it with certain probability so that in the pruned instance, it is active with probability exactly fxe. Here, the choice of f is to benefit our analysis. We shall use the choice of 3xe divided by 3 plus 2xe. After the pruning, we run the greedy algorithm. Namely, each active edge is selected if and only if both of its endpoints are not occupied by other edges yet. Equivalently speaking, for each active edge, it is selected with probability fxe divided by xe if and only if its both endpoints are available. Then we are ready to present the analysis of this algorithm. For edge E between U and V, its selectability is the probability it is selected conditionally on it is active. To lower bound its selectability, we only need to lower bound the probability that it is selected. And that can be divided into two cases. Either U arrives before V and we select this edge when V arrives, or V arrives before U and we choose this edge when U arrives. Since these two cases are symmetric, we only have to discuss one of them. Therefore, here we show how to lower bound the probability that U arrives before V and U is selected by V. Let us call this event V choose U. Namely, when the vertex V arrives, it chooses the active edge before it to the vertex U. Let's denote this by this right arrow. We also can add the condition that TV equals T, since later we can integrate over T and remove such conditioning. Then the probability of this edge being selected is exactly the probability of it being active after pruning times the probability that U is available at time T. This is the first equality. The probability that U is available equals T minus the probability that U is already occupied at time T. This is the second equality. Then, to bound that the probability that U is matched at T, we enumerate the vertex Z that occupies U. We need an upper bound on the probability that U and Z is matched before time T. So this is our goal. The most straightforward upper bound is to upper bound this by the probability that the edge UZ is matched before T. And this equals the probability that the edge UZ is active and both arrives before time T. Therefore, it's fxuz times T squared. Then we sum over all such Z, and from the one regularity of this graph, we know that this summation is less or equal to T squared. Note here we only use the upper bound on the degree of a vertex. If we plug in this analysis to the equation we have above, the lower bound above, we can already get a non-trivial lower bound for V choose U. However, to get a non-trivial selectability larger than 1 over 2, we need a recursive analysis. Note the probability that UZ are matched before T can be further divided into two cases. The first case is that Z arrives before U, and in this case, we need to bound the probability of U choose Z. The other case is that U arrives before Z, and we need to bound the probability of Z choose U. In either cases, we return to the same problem as bounding the probability of a vertex choosing another, but with an extra conditioning that on the arrival time of some vertex. Moreover, there's also the difference that here we need an upper bound rather than a lower bound, because we need to upper bound the probability of UZ being matched before time T. Therefore, if we apply the direct analysis before on this level, we will need a lower bound on the degree of a vertex instead of an upper bound on the degree of a vertex. This is why we need to add these dummy vertices and dummy edges to ensure that our graph is exactly one regular. Finally, we were able to manage to prove that the selectability of our algorithm is 8 over 15. And one can also show that the vertex arrival random order contention resolution scheme cannot do better than 0.567 selectable. It will be an interesting open problem to see if these two gaps can be closed.